Welcome to Challenging Climate, a podcast where we discuss the science, technology, and politics of climate change. I'm Pete Irvin, a climate scientist, and unfortunately, Jesse Reynolds couldn't join us this week. Nevertheless, each episode we bring in a guest with a unique perspective and deep expertise on climate change and put challenging questions to them. In this episode, I spoke with Kerry Emanuel. Kerry is a prominent meteorologist and climate scientist working at the Department of Earth, Atmospheric, and Planetary Sciences at MIT. His research focuses on tropical meteorology and climate change, with a specialty in hurricane physics. He's the author or co-author of over 200 peer-reviewed scientific papers and 3 books, including Divine Wind, The History and Science of Hurricanes. Now, hurricanes are complex weather phenomena. I think Kerry did a great job of explaining what they are, how they form and develop, and how they're expected to change as the planet warms. We also discussed the dangers that hurricanes pose to people in their path, and how he expects this hazard, and our vulnerability to it, to evolve over the coming decades. And stay tuned to the end to learn about the apocalyptic possibility of hypercanes, a phenomenon that Kerry hypothesized that may have played a role in the extinction of the dinosaurs. And now, before the interview, a small request. We've got a core of regular listeners now, but we'd like to see the podcast continue to grow. So, if you're enjoying the podcast and you think others would too, then please recommend it to someone who you think would enjoy it. Thanks for listening, and I hope you enjoy this episode. All right, well, today I have Professor Kerry Emanuel joining us. Jesse won't be here today. He can't make it. So it'll be my first solo podcast. But Kerry, welcome to Challenging Climate.
Well, thank you for having me.
Yeah, could you give us a brief introduction to you and your work? How did you get to where you are today?
Well, I've been involved in atmospheric sciences basically my whole adult life. In fact, I was already interested in it as a child. I taught at MIT for 41 years, and before that at UCLA for a few years. So I've had about a 45-year career teaching meteorology with a focus on the tropics and also on the physics of climate. And I've been on paper retired since July 1st.
Okay, well, thanks for on paper coming out of retirement for this interview. So yeah, I guess your core expertise, or I guess what I sort of know you being famous for, is your work on hurricanes or tropical cyclones. But I think it's first off, it's worth getting some things clear, because I think there's some confusion in the public's mind about the difference between a regular storm, a hurricane, and a tornado. There's a bit of a muddle there. So what is a hurricane?
Well, it's a very good question. I mean, the generic word that covers all the phenomena you just mentioned is cyclone. And so we have extratropical cyclones, aka winter storms. They're the storms that bring blizzards or nor'easters in the wintertime, or just gentle snow. They don't have to be strong necessarily. Tornado is another kind of cyclone, but it's very, very small in scale. Rather than being 1,000 kilometers across, it's maybe 100 meters across, and it has this distinctive funnel shape, and the whole storm is over in a few minutes. It's very fast. A tropical cyclone is, just as the name says, it's a cyclone that forms in the tropics, always over the oceans. It's important that the physical mechanism behind these 3 kinds of cyclones is quite different from each other. So an extratropical cyclone or winter storm is powered by large-scale horizontal temperature gradients in the atmosphere, which are particularly strong in the winter. By contrast, a tropical cyclone is powered by a flux of heat from the ocean to the atmosphere, because the tropical oceans are warm and can sustain a large turbulent flux of heat from the ocean to the atmosphere. That's basically the boiler room for a tropical cyclone. So the physics are very different. You can have hybrid cyclones. Sandy was a good example, which figure out how to draw energy from both the sources that are utilized normally by winter storms and by hurricanes.
Yeah, so tropical cyclones, they only form in particular locations, and they sort of follow particular tracks, so they only exist in certain domains. So where do they form? Are there specific, narrow locations?
Well, there's some broad regions where they form, but basically they form anywhere over the tropical oceans where the tropical ocean temperature is more than about 80 degrees Fahrenheit or 27 degrees centigrade, with the exception that they don't form on the equator and within 4 or 5 degrees latitude of the equator typically. So at the equator, the Coriolis acceleration that results from the Earth's rotation is zero. You really can't have long-lived vortices. But aside from that exclusion, pretty much wherever the ocean's warm enough.
Yeah, then they go on to develop. I mean, I understand there's also not only drivers from the surface ocean, but also from higher up in the atmosphere. That plays a role in shaping their development and how strong they get. Is that right?
That's right. I mean, certainly we know that in models where we can run simulations under very idealized conditions, tropical cyclones will form spontaneously and they'll live forever. You don't have land, you don't have any disruption. But in the real world, tropical cyclones are inhibited by, I would put it that way, by a lot of processes that go on in the atmosphere. The most important of which is wind shear, the large scale airflow in which the storm is embedded changes direction and or speed with height rapidly enough that disrupts the storm, and it has the effect of importing dry air at middle levels into the core of the storm, which is like throwing a bucket of cold water on a campfire. It tends to put it out. Another interaction that is usually unfavorable to hurricanes is with the ocean. And of course, we just mentioned it's sustained by warm ocean water, but you don't have to go very far down in the tropical oceans before the water gets quite cold. And hurricanes churn up that cold water as they intensify. And if they're large and not moving very rapidly, they can do that a lot, and that really damps them down. So there are all kinds of negative influences. But basically, we know now from theory and from models what to expect a hurricane to do if it's completely unmolested by these environmental negative influences.
Yeah, so I've heard that the storms can strengthen and weaken as they go on their course. And then when they hit the land, they typically start to weaken quite rapidly. So what determines that intensification or the power of the storm?
Well, that's a very good question. So in these idealized simulations, or just with pencil and paper in ordinary theory, one of the really important quantities that we use is something called potential intensity. It's a very well-defined thermodynamic quantity. There's an equation for it. It's our sort of E equals mc squared in tropical cyclone meteorology. And it's a function of how warm the ocean is relative to the bulk of the atmosphere above it. Think of it that way. And you can calculate it from just standard, meteorological data or climate data. It's easy to calculate that. What we know is that that serves as a kind of absolute upper bound on how intense storms get. And if you look at real storms, most of them don't achieve this speed limit, if you will, but none exceed it, or not in any appreciable way. The other thing we know is that the rate at which cyclones intensify, again under very idealized conditions, goes up as the square of the potential intensity. In other words, if you double the potential intensity, the rate of intensification would go up by a factor of 4. And once again, most cyclones are molested to some degree by their environments, and they don't make it to these rates. Now, when the storm goes over land, it's all over. There's no more ocean to have a heat flux from. The land can get very hot under the sun, but it's a couple of inches of soil or something that gets hot in the daytime, not nearly enough to sustain a hurricane. And the rate of flow of the heat through the soil and the rock is just way too small. Although there is one interesting exception to that rule. Usually they die over land, although sometimes they can undergo this transformation, which we call extratropical transformation or extratropical transition, in which they start to energize or re-energize using the source of energy for winter storms. That can happen sometimes.
Yeah, that was the Superstorm Sandy. Was that an example where that happened?
Yeah, that kind of happened, that transition happened, but it happened mostly over the ocean.
Ah, okay.
Sometimes the transition can happen. Otherwise, a hurricane's like a fish, it comes up on land, it's going to die. A fish out of water.
Well, I read that you joked that when you retired, you might start up a hurricane safari company. So would you give our listeners a taste of what they would see if they joined you on a hurricane safari flying into one of these storms?
If you go on a normal reconnaissance mission, and most storms in the Atlantic, sadly nowhere else really, are surveyed by a number of reconnaissance missions. First of all, you'd be in an airplane, which is very uncomfortable compared to your normal commercial airliner. There's nobody serving drinks. It's a military looking airplane. And you would go through an awful lot of boring flight hours, even as you start to penetrate the outer part of the hurricane. It just goes dark and gray inside the cabin, and it's like flying on a commercial airliner when it happens to be raining outside. There's nothing to see. There's basically thick fog outside the window. But if it's a strong enough storm and it has a well-developed eye, when you come out into the eye, it's an extremely sudden experience. It's you go from this gloomy darkness, suddenly sunlight, assuming it's the daytime, of course, suddenly sunlight floods the plane, and you find yourself in the middle of a Roman Colosseum of cloud, but it's maybe 80 miles across and a good 10, 12 miles high. And it's something that, of course, have been many photographs taken of the insides of the eyes of hurricanes, but photographs just don't do it justice because you don't get the third dimension. It's like looking at the photograph of the inside of Salisbury Cathedral. Oh, that looks nice. When you go there, you're just completely overwhelmed by it. It's the same sensation of being in a magnificent vault of indescribably large dimensions.
So, on the structure of tropical cyclones, you've got this, I guess, a wide swirl of cloud, and then you have this eye. Like, what's happening here? What's going on to produce that? I presume it's essential to why they work, right? So, what's happening there?
Yeah, if you are in the outside of a hurricane, the kinds of rain showers you get are very much like the sort of rain showers you normally get in the warm, rainy season in the tropics. A cumulus cloud will go overhead and you'll get a big, heavy shower, and then in a few minutes it's over. If you look down from satellite, you do see a difference, though, and that is whereas the normal showers are either sort of randomly distributed or maybe they're in squall lines. In the outer regions of the hurricane, they're arranged in these beautiful spiral arcs that we call spiral bands. And you might notice that from the ground, especially if you know what to look for, but otherwise it's like, oh, it's another shower coming along. It's a very interesting thing from a physics standpoint that these showers can produce very, very heavy rain in the tropics. They rarely are associated with any wind. You might get a few wind gusts. If you're a sailor like I am, you don't worry about tropical showers. They might produce a little bit more wind. And one of the reasons is they're horribly inefficient at converting heat energy into wind, because most of that energy, it's a long story in thermodynamics, gets eaten up when the air inside those cumulus clouds mixes with the dry air outside. What's special about the core, we call it the inner core of a hurricane, is that the air is saturated and filled with cloud on a pretty grand scale. It's not like you've got a cumulus cloud there. It's like the whole atmosphere is filled with cloud from bottom to top and maybe over a distance of 80 or 100 miles. And so there is no dry air for these. There may be convection going on, but no dry air. And in that inner core, you're not losing all of this energy to this mixing. That's part of the reason why the winds are so strong. But the real reason is that it's where the storm is sucking all the heat out of the ocean at a really large rate and converting a big fraction of it into wind energy, much bigger fraction by far than is normal in just a tropical shower.
Yeah, so I guess overall with the storm you have, am I right? You have kind of an indraft running along the surface of the ocean, pulling in moist air that then meets this core, this sort of this wall, and I guess it doesn't get any. I'm not sure why the wall. I presume you can't just go straight up. You need to sort of go up and around.
Yeah.
And then it comes up and then pumps out the top and dehydrates. Is that?
Yeah, and it goes up slantwise. It goes up, it turns, and it goes up, and it goes up and out at about a 45-degree angle, typically. The eye wall is sloping outward with height. I think what's important is that the air already coming into from the outside is humid. And the air, if it then turns and goes up outside the core in a normal shower, if you follow it as it goes up, it may be fractions of a degree warmer than the air around it. So it's not very buoyant. It's a little bit buoyant. An ordinary tropical shower actually isn't a thunderstorm. Lightning is pretty rare in the tropics. To get lightning, you need a strong updraft,
Mm.
10, 15 miles per hour. Normal updrafts in tropical convection, and this goes for the spiral bands of hurricanes too, is somewhat less than that. Now, the important thing is that the air that goes up the eye walls had a lot more water added to it from the evaporation from the ocean, which is very strong when you have very powerful winds like that. And so the air going up may be 10 degrees centigrade warmer than the air in the environment, not a fractions of a degree. And so it's going up faster, but basically it's responsible for the fact that you have much stronger winds at the surface.
Well, I guess that brings us on to the dangers that hurricanes pose. So, what are those dangers as a hurricane rolls in towards your city? What could you expect to happen?
Well, one of the most important things I have to say about that, and you'll hear that from anyone you ask the same in my profession that you ask the same question to, is that the real risk, the thing that typically kills people, isn't wind, it's water. Now, there are two sources of water. There's water coming in from the ocean in the form of something we call a storm surge. Now, I wish we had a different name for it. It could be called a wind tsunami to distinguish it from an earthquake tsunami. It's exactly the same physics. And a lot of people listening to this program will have at some time seen these horrible videos that were taken in the tsunamis that affected Indonesia and then later Japan. And you know that if you see that, you're not going to be able to survive it. In a hurricane, it's the same physics and the same phenomenology. It's this inward rushing water, but it occurs in the middle of a ferocious windstorm as well. So you don't really stand much of a chance if you have a strong storm surge. And that's the main reason that we typically ask coastal residents to evacuate in the face of a hurricane. To give you an idea, a storm surge associated with a tropical cyclone in the Bay of Bengal in 1970 that went up into what was then called East Pakistan and is today called Bangladesh killed about 500,000 people. Now, we get upset, as we rightfully should be, when 1,000 people die in Hurricane Katrina. But this is 500,000 people, all from the storm surge, because they had no place to go, no place to hide, no vehicles to get anywhere. This is really bad news. And when people try to envision the risks to themselves in a hurricane affecting the US, they usually mistakenly think of wind. Now, wind isn't to be tampered with. There's all kinds of horrible things flying around, and if they hit you, you're dead. But usually your house, if you're in a reasonably strong house, it will protect you from those things. Not always. If it's not a strong house, it'll just blow over. The other source of water is, of course, torrential rains. And we saw that with Hurricane Harvey in Dallas. You just get unimaginably heavy rain for a long time, and you have everything from water rushing down creeks to just, a fairly rapid rise in stagnant water level in city streets and things. Either way, it'll kill you if you have no place to go. So the real dangers are from water, which is not to completely downplay wind, but if you look at mortality in US hurricanes, it's mostly water.
Yeah, because I guess one of the things is not so much true with Harvey, but I remember hearing with Katrina, and I guess it must be the case with this Bangladeshi storm as well. The damages of tropical cyclones really depend on their path. It's not just about the intensity of the storm, but obviously that matters. But if your path is such that you line up with, I guess, the Bay of Bengal or line up with, on New Orleans, the storm surge is fairly concentrated, right? And it depends on the path, the direction it takes into the land. Is that right?
Absolutely. And there are two things about the path that we worry about. One is sort of obvious. Is it going to hit a major population center? Back in 1999, there was Hurricane Brett in Texas. Now, I bet you not very many people listening to the program, unless they happen to be from that part of Texas, even remembers that. It's not in the record books. It was a ferociously strong, very high category hurricane. Basically, it went into farmland, and most of the fatalities were from cows rather than people. So we don't remember it. Whereas a Sandy that went right into New York City or Katrina that went right into New Orleans, that makes a heck of a difference. But now we come back to the point you raised, which the surge, which is usually the main killer, or often is, depends on a lot more than just how strong the winds are. It is, to start with, very sensitive to the diameter of the hurricane. And hurricane, people don't know this, hurricanes come in lots of different diameters. Sandy was a whopper. Sandy wasn't even a hurricane when it made landfall. It was a tropical storm, but it was the largest in diameter that's ever been seen in the North Atlantic Ocean. And that meant that it created a very large storm surge, even though the wind speeds weren't enough to write home about, really. So size matters when it comes to storm surge. The other thing that matters is the shape of the coastline, whether they're bays, for example, which tend to funnel the surge and amplify it. And very importantly, how rapidly the water gets deep as one moves offshore. And if the water is very shallow offshore, which it typically is, for example, off the coast of Texas, that makes for a much larger surge than if the water gets deep rapidly, which it tends to do, for example, off of Miami. So surges are sensitive to all those things, and a small change in the track or the intensity or the diameter of a hurricane can make big differences in the surge.
I guess there's always another matter of luck, really, is how high the tide is at the time. I presume that's something that's completely independent of the climate. It's just if you're lucky, it's low. If you're unlucky, it's high.
Exactly. And it's particularly true in places like New England, which have a pretty respectable tide range. Here in Maine, where I am, it's 10 feet or so. Other places, South Florida, the tide's not that great, so it doesn't matter as much, but it always matters to a degree.
I was having a look at the societal impact of tropical cyclones, and I think you might know this stuff better than me, but I get the sense that the number of lives lost in tropical cyclones seems to be falling over time. And potentially also, I mean, I saw a study or two that looked at the economic damages, and this was hurricanes in the US that looked at, and found that they hadn't been changing. I think that might surprise a lot of people, given that climate change is going on, and as we'll talk about in a minute, this is changing tropical cyclones. So yeah, what are we doing right that's reducing the impacts of tropical cyclones on people? Or do you contest those claims I just made?
Well, there's no question that around the entire world, not just in the US, the number of people, number of lives lost in hurricanes has dropped precipitously. And I have to say, it's one of the most gratifying things I've seen in my professional life. And there are a number of reasons for it. I would put at the top of the list just far better warnings, by which I mean better forecasts. The forecasts have improved immensely over the last 50 years, no question about it. But in tandem with that, just the whole methods by which civil authorities go about preparing the population for the storm that's bearing down on them, whether it's evacuating people or putting them into shelters, what have you, they've gotten better and better and better at that. And people have become more and more educated. There are fewer and fewer people who say, well, I'm just going to stick out this storm. I'd stick out the last one. I was fine. That's happening less and less. And not just in the US, right? But there are other things. This horror story I mentioned in Bangladesh, in East Pakistan, isn't going to happen again for the simple reason that lots of NGOs have gone in the meantime and built many hundreds of elevated, simple concrete storm shelters that now it's basically true that they're within walking distance of most of the coastal population. So, and it's happened 2 or 3 times. We've had worse storms meteorologically, but far fewer deaths because A, people are told that's coming, and B, they have a place to go. They don't need a car to get there. So the strategies are different from different places. In the countries in Central and South America, it turns out that the last thing you want to do is send police to people's houses to tell them to evacuate, because they're much more afraid of what the police will do than what the hurricane might do. But if you send the priest to the door, people will listen to that. So it's culturally dependent. Now, as to the damages, globally, there's no question that they've been going up very quickly. However you normalize it, as fractions of the GDP and so forth have been going up. It's less true of the United States for the simple reason that the normalized damages haven't been going up much in the US. The absolute damages have been going up a lot. By normalized, I mean that the huge source of increasing damage in the United States and in some other parts of the world is just increasing infrastructure at the coast. people are moving from inland to the coast like lemmings. The coastal population all around the world is increasing much faster than the total population. So we're having a lot more people at risk of hurricanes. That's driving it up. If you normalize for that, you still get big increases in most places, but not in the US. And for various reasons, the storms striking the continental US have not gotten appreciably worse, even though they have around the North Atlantic as a whole. So that's one factor. But around the world, and even if you just take the North Atlantic, but take all the coast, not just the US, the damages are increasing however you normalize them.
Well, let's get to that. So, yeah, have hurricanes been changing as the world warms, and how can we expect them to change in the future?
Well, this is a very interesting and complicated issue. I mean, and to begin with, even if the climate weren't changing, there are natural phenomena that affect hurricane activity. In the Atlantic, a prominent one is El Nino. During an El Nino year, you tend to have suppressed activity, and during a La Nina year, it can be very active. Now, this particular year is a big exception so far. It's a La Nina year. There should be a lot of storms, and there are far fewer than normal so far. Let's hope it stays that way. But normally in an El Nino year, you have suppressed activity. So we sort of know about those natural climate fluctuations. Now, the big problem for the US is there has been, on top of these natural things, a huge uptick in North Atlantic hurricane activity since 1980. The bulk of which we don't think has anything to do with global warming, although that does affect hurricanes, but to another man-made climate phenomenon, which is the sulfate aerosols. And it's a long and interesting story, but sulfate aerosols are created from sulfur that's part of the products of burning fossil fuels. And as fossil fuel combustion ramped up from the 1950s to the 1980s, there was a colossal increase in sulfur emissions. And sulfur gets, through a photochemical process, turned into little aerosol particles that we see as a kind of haze. And older people who grew up in the eastern seaboard will remember that you didn't have a hot and humid summer day without it being incredibly thick haze in the US. And that had deleterious effects, created acid rain, for example, which killed plants. And for that reason, there's a whole bunch of legislation in the US and also in Europe, which had the same problem, that very rapidly ramped down these sulfur aerosols. So they sort of peaked in the 1980s, and now they're back to where they were more or less in the early 1950s or late 1940s. So the aerosols ramped up and they ramped down. And with that, the hurricane activity did the opposite. They ramped down and then they ramped back up. So we had a hurricane drought in the North Atlantic in the 70s and 80s. And we've only recently figured out how that all happened. The sulfates are part of the story, but the big thing was the European sulfates were shutting down, and there's a whole literature on this, the African summer monsoon. Every summer it rains a lot in the Sahel because of a monsoonal system that has to do with the Sahara Desert getting very hot, basically, in the summer. European aerosols were shading or slightly reducing the sunlight getting into the Sahara and shutting down that monsoon. And that led to spectacular droughts in the Sahel in the 70s and 80s, which led to much more dust being lofted in the atmosphere. So there are a lot more dust storms that are carried westward by the trade winds out over the tropical Atlantic. And they're highly reflective dust particles. So those combined with the sulfate itself cooled the Atlantic. And, this is very obvious in measurements of ocean temperature. That cooling of the tropical Atlantic suppressed hurricanes. So we saw this big suppression, and it was during the 70s and 80s that we experienced in the US this colossal increase in coastal construction during this quiet time. And then the hurricanes came roaring back after the Clean Air Acts were passed. I'm not suggesting we shouldn't have passed those Clean Air Acts, but that silver cloud had a black lining in the form of increased hurricane activity. And the hurricanes today are, of course, coming ashore where there's far, far more infrastructure than there was in the 1950s. That's been a big problem for us. Around the world, we're only beginning to see now in observations the long predicted signal that hurricanes should be becoming more intense because of global warming. And not the largest effect in the world, and hurricanes aren't exactly common, so you have to accumulate a lot of data. But now we're beginning to see that in the data. So there's global warming on top of everything, but the global warming hasn't been the big story for Atlantic hurricanes over the last 50 years. It's been more this sulfate, another man-made effect, but sulfate-induced changes.
Oh, that's interesting. I mean, I guess I'd heard it in the context of, European and North American sulfate aerosols create a cooling that was predominantly in the Northern Hemisphere. And
Yeah,
that shifted the intertropical rain belt, the ITCZ, Intertropical Convergence Zone. I guess it shifted it southwards, which dried out the Sahel. I hadn't heard the connection about the increased aerosol or dust aerosols that would then have that cooling. Was there anything to do with that hemispheric balance, the fact that we're cooling the north more, or was it just the direct cooling on the ocean that?
it's both, but in terms of this quantity called potential intensity, which is a big influence on cyclones, a regional cooling will have a much stronger effect than a global cooling of the same magnitude. That has to do with the physics of hurricanes and so forth. But just cooling the North Atlantic by itself without cooling a lot of the rest of the globe, which is what was happening, giving a very strong effect in suppressing hurricanes. Whereas if you had cooled the whole globe by the same amount, you would have seen a little bit of a decline, but not nearly so much. And of course, cooling the northern hemisphere relative to the southern hemisphere also has an effect in suppressing northern hemisphere storms and enhancing southern hemisphere storms.
Yeah, just want to elaborate a little more. I mean, yeah, hurricanes are they seem like one of the trickiest parts of the climate problem to predict well or observe well because they are so fairly infrequent and they're very unique in their character. I think we were talking about that the nature of the damage they do really depends on the type of storm, the way it went, etc. So it's quite hard to pick out some of the trends. It's interesting that you said that the biggest dominating factor had been the sulfate aerosol pollution, but there are some things that we expect to happen as the planet warms. Now we've sort of cleaned up the aerosol pollution. I think did you mention already that we expect an intensification of storms with global warming?
Yeah, that's for the simple reason that this upper speed limit, potential intensity, goes up as you put carbon dioxide into the atmosphere. It means that the oceans can't lose as much heat by infrared radiation, so they have to lose it by evaporation. Evaporation cools the ocean and the energy gets put into the atmosphere. So you need more evaporation. To get more evaporation, you need more potential for evaporation, more of a difference between the ocean and the atmosphere. And that is a big factor in the potential intensity. So that's been predicted for now 35 years, going on 35 years that we first predicted that potential intensity would go up. There's no question the potential intensity is going up. You don't need a hurricane to calculate that. You just need climate data. But now we're beginning to see the hurricanes follow suit.
Yeah. And there's some other changes that we expect or we're beginning to suspect that we're seeing with tropical cyclones. Could you run through some of those? Or should I try and
Well, no, I think the big deal actually isn't so much the increase in wind, although it is something to be reckoned with. It's the increase in rain. So the rainfall goes up very fast with temperature, and it's a very simple piece of physics. Basically, warm air holds more water vapor than cold air. So as you warm it, you actually double the amount of water vapor for every 7 degrees centigrade of temperature rise. So just a few degrees of warming will importantly increase the amount of water going up into hurricanes, and that increases the rainfall. And that, of course, is a big contributor to the increase in flooding. The other problem that's worrisome is the general rise in sea level due to global warming. It hasn't been that much so far, but it's noticeable. Talk to people who live in Miami Beach, they'll tell you all about it. And so when that hurricane arrives, especially at high tide, the storms are just riding on top of higher water. This is a big contributor to Sandy's surge in New York. New York is a little bit special because, well, a lot of cities around the eastern seaboard, that the sea level was rising faster, if you will, in New York than a lot of other places because of an interesting effect having to do with the disappearance of great ice sheets in the last ice age as a rebounding effect. Anyway, it's a long story, but the sea level was in general about a foot higher when Sandy hit than it had been 100 years earlier. And so if Sandy happened 100 years earlier, it might not have flooded lower Manhattan.
Yeah. I guess another change I'd heard, I'm not sure if it's as settled, was potentially demonstrated in Harvey. Because if I remember right, Hurricane Harvey was not only very rainy, but it was also very slow. It sort of sat on top of Texas for a long time. Am I right that there's a prediction that hurricanes should be slowing down? They shouldn't be traveling north as fast?
Well, it's controversial. If you talk to my colleagues, they'll all tell you that. There is some data suggesting that they're slowing down. My own analysis of it, which is just mine, and it is not necessarily the right answer, is that there's, at least in the North Atlantic, they're slowing down in the subtropics, around 30 degrees latitude, but not so much in the deep tropics or at higher latitudes, or they're expected to slow down because of global warming. Harvey, of course, was in the subtropics. It was close to 30 degrees latitude. So, but I think the jury is out on that. It's not quite as settled as all that.
Yeah. So I guess overall, as the world warms by another, we're at 1.2 odd now, as the world warms to, say, 2 Celsius, do you expect the overall impact of hurricanes to increase, or do you expect economic developments and further improvements in weather forecasts to offset those physical changes in the storm?
Yeah.
What's your bet?
My bet is that mortality will continue to fall because we're getting better and better at warning people and getting them out of harm's way. Also, we're beginning to see some encouraging movements toward this ridiculous subsidy that the US basically giving for people to move into risky places. That's a long story, and it's probably the most influential story about hurricane economics in the US is these policies. They're beginning to relent. Insurance rates are gradually going up in coastal regions, so people are a lot less likely to move there. So the mortality story is, I think, a good story for the most part. On the damage side, I'd flip that around and say it looks like there's going to be a lot of destruction. And the basic point here, people say, well, the hurricanes aren't changing that much. And that's in some normalized sense, they may be right about that. The problem is that all of society, whether it's a relatively well-developed place like the US or some less developed places such as you might find in the Caribbean, they're pretty well adapted to events that occur maybe, once every 100 years or more frequently. They just are. It doesn't pay for them to build for less frequent events. So the real problems happen to societies when something that used to be a rare event, like a 200-year event, are suddenly 50-year events or 20-year events. Whether it's flood or wind, it doesn't even matter. It's that shift in this return period that societies can't adapt that quickly to this sort of change. Infrastructure evolves slowly over time, even in highly developed places. So I think, unfortunately, we see more damage. Now, we have to be very careful that this is not globally uniform. My own methods show that there are parts of the deep tropics which will probably experience fewer and weaker hurricanes. So you can't make a universal statement about how they're going to change. In general, we see the biggest changes in the subtropics and the middle latitudes, the biggest increases in risk. But we see declining risk in some other parts of the deep tropics, depending on where you are. That, of course, has to still be researched, but it's for sure the case that it's not a uniform change. Not everywhere is going to experience worse hurricanes.
So I'm going to try and segue here, but we have at the moment 5 categories for tropical cyclones based on how intense they are. Do we need a 6th?
Now, we need to get rid of that system altogether, and a lot of my colleagues are agitating for that. It's a bad scale, it's outdated, and it doesn't recognize the most important fact is that the danger of hurricanes is from water, but the Saffir-Simpson is a wind scale. It's a wind scale. So people get hung up, and insurance policies are written depending on what category, has to be exceeded for your policy to kick in. It's all nuts. It's just got to go. And we need something more sensible that's tailored to the storm. I kind of like the British system. You have a yellow alert, an amber alert, and a red alert or something like that. I can't remember what the 3 are. And it basically is a direct measure of the risk to you, regardless of what element of the storm that risk is coming from. So I think three lights or 3 colors together with a very, very well thought out, short, crisp narrative, an actual narrative written by a human being, not a robot, that tells you what the risk is and what you ought to do. And just get rid of Saffir-Simpson. It's useless at this point. It's caused a lot of problems. I mean, my favorite story, gloomy story, the real one, is that Sandy was bearing down on New York. The National Hurricane Center demoted it from a hurricane to a tropical storm, which caused the mayor of New York City, Michael Bloomberg at the time, to cancel an evacuation. Now, to their credit, the Hurricane Center and NOAA, the government, realized their mistake and called up the mayor and said, don't do that, don't do that. But it just shows you how many terrible mistakes have been made because of the way we categorize storms. So forget category 6, Peter. Forget all the categories. It's time to move on to a more sensible way of warning people.
Yeah. Yeah, because I think another example, Katrina, I think, was a category 3 when it made landfall, and yet was one of the most deadly in US history. Well, I was trying to segue from hurricanes to something much more intense. You wrote a paper in 1995 that caught my eye. I thought it was really interesting. It's titled Hypercanes, a possible link in global extinction scenarios. So what is a hypercane and how might it have led to mass extinctions?
Well, the hypercane started out as a singularity in a mathematical equation. That is, if you look at the formulation of the mathematics behind potential intensity, it's all very well behaved until you get to a critical ocean temperature. And beyond that, the heat engine kind of runs away. It's very interesting. If you lower the surface pressure, which is what you're doing in the middle of a hurricane, it turns out that means you can add more heat to the air. And so you add more heat, the pressure gets lower, then you can add even more heat. That's a positive feedback. And that's true. In fact, strong hurricanes are maybe twice as strong as they would be without that feedback. But if you make the ocean hot enough, the feedback runs away and you can't control it. And then what we discovered by computer simulations is that it kind of transforms itself into a different beast, somewhere halfway between a tornado and a hurricane, that also goes very deep into the stratosphere. And today's hurricanes may go a little bit into the stratosphere. These go very deep and pump a lot of water up there where it doesn't belong and where we don't usually find it, which interacts with ozone to destroy it. And that was the basis of the paper. Now, the fact is that you need water temperatures in excess of 50 degrees C to get one of these. It's not going to happen from global warming. There's no reason to worry about it. What we thought at the time was, well, if you wanted to have one of these things happen, you could have an asteroid impact with the ocean that would superheat it over some region, or maybe undersea volcanism. But something extraordinary would have to happen. Now, I just learned last week, because I was reading papers outside my field, that the geologists have now figured out from fossil evidence that the Chicxulub impact, which is thought to have been responsible for the demise of the dinosaurs and was partially in the ocean, probably heated seawater to about 70 degrees C over about a 200-kilometer radius patch. And so I've been thinking maybe we better try to actually simulate one of these things. But we argued that it may have been contributing to mass extinctions by doing away with the ozone layer. Science fiction, but it's science fiction that's based on these known physics.
So you wait ages for a world-ending disaster to come along, and then well, I guess it's 3 of them at once. You've got the asteroid itself, the hypercane, and then you have, I think, with asteroid-type impacts or even big eruptions, you have this sort of nuclear winter-style cooling that
it's not fun to be around during a mass extinction event, for sure.
Well, rather than ending on mass extinction, we usually end by asking, what makes you hopeful for the future? What makes you optimistic?
When you ask that question, Peter, do you mean the future of the climate, future in general? What?
This is challenging climate. So we usually talk about climate, but if you want to go broader, that's fine. That's up to you.
Well, I'm optimistic that maybe too late and too slowly, we are going to actually start to move, and you can see this happening on climate change. There are little things. The fact that people are buying up electric cars much faster than anybody thought. In fact, production can't keep up with it. California has basically said we're not going to build any more internal combustion engines after 2035. the environmentalists are finally beginning to back down on their opposition to one of the surest ways of transforming energy, which is nuclear power. I'm very optimistic about that. It's been a big sea change. And we continue to really advance renewables and storage. So and not just in the US, but maybe in some ways faster and more importantly in other parts of the world. China is moving on this, Russia even. And so I'm optimistic that we will do it. Now, whether it's going to be fast enough to spare us some really bad things, I don't know. But it's certainly a lot more reason to be optimistic than not too many years ago.
Excellent. Well, thanks a lot for taking the time. This is a really interesting discussion.
Yeah, I enjoyed it, Peter.
Well, thanks for listening. Please rate or review us on Apple Podcasts and elsewhere, and consider supporting us on Patreon. That's patreon.com/challengingclimate.